If you're also a calculus teacher, then you know, once you finish teaching the power rule for derivative, then no student wants to use the definition of derivative anymore. But it's okay, because I have 2 videos addressing that issue already. Links will be in the description for your convenience. Today, let's talk about another issue, and that is L'Hopital's rule. You know, when students learn the L'Hopital's rule, they just want to use L'Hopital's rule for all the 0 over 0 or infinity over infinity cases. That's why I have this for you guys. We have the limit as x approaching infinity of the integral function, integral going from 0 to x, absolute value of sine t e to the cosine t dt over x. Well, let's investigate what's going on the top first. When we put infinity to here, let's see the integral going from 0 to infinity, absolute value of sine t e to the cosine t. What's up with this? I will tell you, usually when we have absolute value, I think it's safe to look at its graph first. So I will show you guys the graph. The graph is going to look like this. It will start at 0, and it's going to go up like this, and then like that. And this is when t is equal to pi, because sine pi is equal to 0. And after that, it's supposed to come back down. But because of the absolute value, it's going to make that part positive. So you will get a nice reflection like this, and then that. This is the first period going from 0 to 2 pi. This right here being pi. After that, you just pretty much have the same thing over and over again, and then so on, so on, so on. So, if you want to get the integral from 0 to infinity, you can just look at this graph. We want the area under the curve from 0 all the way to infinity. Well, of course, this is always the same. I don't care about how big this number is, right, for the area. But we are just adding infinitely many of them. This right here will give us infinity. Okay, I will still find the area for you guys legitimately, right? Check this out. Here is the first copy. This and that are the same. So let's go ahead and just find this right here real quick. And that is going to be the integral going from 0 to pi only. On this interval, this function is positive, so we don't need the absolute value. So we have sine t e to the cosine t dt. Integrating this, we can just put u to be cosine t. The derivative of cosine t is negative sine. This is positive sine, so the answer will be negative. So we have negative, and we integrate e to the u, and we just get e to the u back. U is cosine t, so we have this. And then go ahead and plug in. Plug in pi, plug in 0, so we get negative e to the cosine pi minus negative e to the cosine 0. Cosine pi is negative 1, cosine 0 is 1, so this right here is negative e to the negative 1. Minus minus becomes this plus. Cool, huh? And then e to the first power. Just like that. So this value, you have infinitely many copies of it, of course you will get infinity. Cool. So the top is infinity. The bottom, of course, is infinity. Look, this is infinity over infinity. So that means we should be able to apply L'Hopital's rule, right? Okay. If we want to use L'Hopital's rule, then the top, go ahead, take the derivative. The bottom, go ahead, take the derivative. Alright, so we are looking at the limit as x approaching infinity. On the bottom, that's easy, it's just 1. But how about the top? How do we take the derivative of an integral function? Well, fundamental theorem of calculus, part 1. It says derivative and integral cancel. And it looks like we can just plug in x into the t's here. Okay, so we get, just kidding. We get sine t, but t becomes x. I was kidding, sine x. And then e to the cosine x. Do we maintain the absolute value? I have never seen that case before. Because remember the good old Calc 1 day, if you are differentiating an integral function, let's say from 0 to x, it doesn't matter like how crazy this thing is inside. take the derivative of this is always going to be the easiest because you just have to plug in x into all the t's. So the answer for this right here is just e to the x squared over 1 plus x to the third power. And this is the question that you should never miss on your calculus exam. But here we have the absolute value. Do we maintain the absolute value? It's tricky, huh? Well, let's see. Suppose we don't, then this right here, observe the limit as x goes to infinity. Well, this graph is pretty much like this, but it does go down, right? It does go down. It has the negative part right here. But you can see that as x approaching infinity, it will not give you a horizontal asymptote. So that will be does not exist. And even though you attach the absolute value, which you have the graph like right here, you see you still don't have any horizontal asymptote. So this right here does not exist. So does that mean the original limit doesn't exist either? No. In fact, we cannot do the following. If we use L'Hopital's rule, if this limit does not exist, we cannot necessarily say the original limit doesn't exist either. It's not necessarily true. So how are we supposed to take care of this? You see, this right here is a legitimate example where you cannot use L'Hopital's rule, even you have infinity over infinity. So how do we do it though? Well, check this out. Still refer to a picture. Picture would be the best friend right here. Instead of going from 0 to x, right? Let's say x is somewhere right here. Just say this is x. But instead of looking at this from 0 to x, you see, before x, you will have so many copies of this. So let's break this down. I want to see how many copies of 2 pi that I have before this. So I can take a look at x being equal to 2 pi. I want to look at the whole thing right here times some number n copies of 2 pi. All right. So in this picture here, we have just one copy, but if x is far away, then we have more. But of course, we still have that extra part. So what do we do? It's okay. For this part, let's just say plus some small constant k. Now check this out. I put down from 2 pi n, but this is only from 0 to pi, and that's this, right? So let me indicate that this right here is e minus e to the negative 1. Very nice number. This and that have the same area. It's just like a reflection. So together, from 0 to pi, we just have 2 of them. Just like that. Very nice. Now, what's k though? Firstly, I want to make sure that k is in between of 0 to 2 pi. So I'll just indicate that right here. K is from 0 to 2 pi. Not including 2 pi, right? So that may be like from here to here, like pi over 3 or something. Doesn't really matter that much. You will see. All right, I think we are kind of ready to go. Let's have a look. I will come back here and make a little change of variable. Instead of saying x approaching infinity, I will just say perhaps right here, this line first, I will just say let x equal to 2 pi n plus k, where n is just an integer and then k is a number between 0 and 2 pi. And then we will see that this right here is the limit, as if x is going to infinity, that means n better go to infinity as well. If we have x far away, that means we have more and more copies of the 2 pi. So n goes to infinity. Well, I can just put that down for the bottom. So the bottom we have 2 pi n plus k. Put that right there for the x. So we have the integral going from 0 to 2 pi n plus k. Absolute value of sine t e to the cosine t dt. Nice. Now what? let's break this down into two parts. The first part is when we end exactly at the multiple of 2 pi. So this is going to be limit as n goes to infinity. So the bottom is just 2 pi n plus k. On the top, let's go ahead and write down integral from 0 to 2 pi n. And then we have that, let's just write it down again. So integral sine t e to the cosine t dt. And then we have to add the integral starting from here, 2 pi n, up to 2 pi n plus k. And then write down the function one more time. So integral of absolute value sine t e to the cosine t dt. Perfect. Now, how do we figure out this value? In fact, we know it already, because this right here is just n many copies of this thing, right? So each copy is that we have n copies of this. So this part is just going to be this number multiplied by n. So have a look. This right here will give us the limit as n goes to infinity. Let's write that down first. 2 times e minus e to the negative 1 times n. Very nice. Now, how about this? Integral going from 2 pi n to 2 pi n plus k. It's just like this area here. Well, I will tell you, it doesn't really matter what it is because this is always going to be finite. Not only that, it's always going to be less than this number. So depends on how you want to write it. I will just say maybe plus some alpha value. Yeah, alpha for area. And the alpha here, just denote that it has to be in between of 0 and that. So 2 times e minus e to the negative 1. So it's just finite. That's all you care. And then on the bottom, we still have that 2 pi n plus k. Okay, now do we see it? Yes, because the top is actually just a linear function in terms of n to the first power here. That's just a number. And then on the bottom, same thing, n to the first power. So of course, we can ignore that because n goes to infinity. And once we ignore this, n and n cancel, 2 and 2 cancel. So ladies and gentlemen, what's the final answer? The final answer is very nice. Look, e minus e to the negative 1 over pi. Just like that. Again, n and n cancel, 2 and 2 cancel, and that is what we have. I have never done this kind of limit with you guys before. This is super, super cool. Let me know what you guys think. That's it.